Hey guys, welcome back. So before we get started, I want to say a couple words about some things that are changing. So I told you in my welcome back video that we're going to do office hours with a Google Hangouts meet um, on Monday and Wednesday from 3 to 4 p.m. We're going to change the Monday. We're going to leave the Wednesday 3 to 4 p.m. But if you want to meet for live Q&A, we're going to move the Monday Google Hangouts meet to 11 a.m. And I'll put a note about that on Classroom. But I was asked to kind of switch things up a little bit so that we're not meeting at the same time each day, just to accommodate other classes that have to meet and students who have siblings that might need that afternoon time. So hopefully that works for you. Um, Let me know if you just can't get to either one and you really need to ask questions live. We'll figure something out. We'll make it work. Um, so what we're going to do today is talk a little bit about the last set of notes that you took. Well, over the break probably, or at some point hopefully. The very last post on Classroom was this spontaneity of reactions notes that you see kind of behind me here. You should already have those. If you don't already have those, go back and watch that YouTube video from March 12th, maybe something like that, somewhere in there, right before spring break. And then we're going to talk today about kind of a few extension problems and uh, with delta G and spontaneity. And then going forward for the rest of this week's assignment, we're actually going to have you guys preview the next topic by doing a little bit of online reading, and I'll explain that later on. So let's start off by talking a bit about spontaneity. Again, you kind of read about this, or excuse me, took notes about this already. Um, but the spontaneity of a reaction just means, does it happen on its own? Does it take a lot of help? Are the products favored? Is another way that sometimes you'll hear it said. Um, Essentially, does the reaction proceed in a forward direction without a lot of help? Okay. Um, and we even did some calculation in addition to talking about entropy, which is just randomness. We got into doing some calculations of free energy. So you get this equation, delta G equals delta H minus T, temperature, times delta S. And if our answer, when we do that calculation, pretty simple little calculation, is if it's negative, you have a spontaneous reaction, one that happens without the need for a lot of help. Um, and so here's an example, that I did in the video. We figured out that essentially the combustion of methane is spontaneous, which is exactly what we would expect, because of course it doesn't take a lot of outside help to get methane to burn. Burns very much on its own with just a little bit of a spark to start it off. All right, and so if you remember also all of these numbers, this negative 393.5 for the delta H of carbon dioxide and the negative 241.8 kilojoules per mole for the water, all came from a table that I gave you guys. Looks like this. Well, this is the front side, but the back side looks like this. If you don't have that table, I'll make this one available again by PDF on today's classroom post. And so if you can't print it off, maybe you can have it open and just kind of bring it up as needed throughout the notes. Um, okay, so we know how to calculate delta G. It's pretty simple. Once we know our delta H and our delta S and our temperature, as long as we make sure to get our temperature in kelvins, we should be good to go. And if our answer is negative, it's a spontaneous reaction. What I want to talk about today is the same equation, delta G, Gibbs free energy, but now we're going to talk about it in terms of okay, so what happens if we have a reaction that is what we call conditionally spontaneous. And you probably want to write this down, so pause at any point and write down the question. But it says, is the following reaction always spontaneous, always non-spontaneous, or conditionally spontaneous? And what we mean by that is that temperature is, of course, involved. And when temperature is involved, we can sometimes have, some reactions are spontaneous at high temperatures, some reactions are spontaneous only at low temperatures, other reactions are always spontaneous regardless of the temperature, and others still are never spontaneous regardless of the temperature. Okay, and if you look at our equation, see if we can kind of make sense of that. Delta G equals delta H minus temperature times delta S. And that equation hopefully makes a little bit of sense with what I just said, because if we need delta G to be negative in order for the reaction to be spontaneous, let's say that we have a negative delta H. So negative 700 kilojoules or whatever it is. Let's say that we have a positive change in entropy, delta S. So usually it's a smaller value because entropies are just smaller. But so let's say it's positive delta S of 0.25 or something like that. Well, what we're doing then is we're taking a negative and we're subtracting a positive, because temperature is always positive because it's in kelvins. And a positive temperature times a positive change in S will give me a positive number. So again, a negative delta H minus a positive will always give me a negative answer. And a negative delta G means the reaction is spontaneous. So regardless of the temperature, the Kelvin temperature, this is going to result, anytime I have negative delta H and positive delta S, it's going to result in a spontaneous reaction. And the reverse is true. If I had a positive delta H and a negative delta S, the opposite would be true, right? You have a positive minus what will be a negative. So essentially a positive plus a positive, which will give me a positive delta G. And if it's a positive delta G, it's a non-spontaneous reaction. Okay. Then the last part of the question, so we're trying to figure out, is it always spontaneous? Is it always non-spontaneous? Or is it conditionally spontaneous? Conditionally meaning it depends on the temperature. And the only way that it's going to depend on the temperature or be conditionally spontaneous will be if we have, for example, a positive delta H and a positive delta S. All right, because then it just depends on the temperature. If I have a positive delta H minus another positive number, it could give me a negative answer depending on the size of those two numbers that I'm, my first and my second number that I'm subtracting with. Or it could be, could be positive, could be negative answer. The same thing is true if they're both negative. If I have a loss in enthalpy and a loss in entropy, my answer, depending on the temperature, could be positive or negative. Okay, so let's take a look at this reaction. If the reaction says, is the following reaction always spontaneous, always non-spontaneous, or conditionally spontaneous? So the first thing we're going to have to do is figure out the delta H for this reaction. And remember that we're going to go to the table and we're going to use products first, all right? So I have aluminum, which is an element which should have 0 heat of formation, and sure enough, there it is, 0. So that's going to be, I could say 2 times 0, but I'm just going to say 0. So 0 kilojoules plus my other product, which is iron 3 oxide. So let's see if we can find our iron 3 oxide. Let's see here, Fe2O3, so negative 825.5. All right. So negative 825.5 kilojoules. So those are my two products minus my reactants. So I have my first reactant is aluminum oxide. So again, going to the table, we've got aluminum oxide, which is negative 1676, so pretty huge heat of formation. Okay, and then I'm going to add that, well, to 0, right, because iron is going to be an element, so its heat of formation is 0. Okay, and I'm going to go ahead and just kind of do this for you just to speed things along, because the addition and multiplication is not really the main thing we're trying to learn here. But it gives me a positive answer here. It's 850.5 kilojoules. So based just on that alone, we might guess that this reaction is going to be non-spontaneous because it's an endothermic reaction. We have a positive delta H. But of course, enthalpy change is not the only thing that determines, whether a reaction is spontaneous or not. So let's also look at entropy. So for the entropy, we're going to again start with our products, aluminum, and aluminum has a relatively small entropy value of 0.028, but we are going to have to multiply that by 2. So 2 times 0.028 kilojoules, and we're multiplying by 2 because, of the coefficient. And then we're going to that, we're going to add the iron 3 oxide. And again, let's see here, iron 3 oxide is 0.087, 0.087 kilojoules. So those are my two products, and then products minus reactants, just like with enthalpy. So now my first reactant, aluminum oxide. Back to the table, and it looks to be 0.051. These are all solids, so that's why there's such small entropy values. Solids tend to be more or less pretty ordered, right? And then I have 2 of my iron, which come down here, Fe 0.027. All right, so 0.027 kilojoules. And again, not going to worry too much about having you guys do the math. I'll do it for you. Just a bunch of multiplying, adding, and subtracting. And I got 0.038 kilojoules. And I'm sorry, actually that's kilojoules per Kelvin. I left off the per Kelvin part of my entropy values. And then, so the question is it always spontaneous, always non-spontaneous, or conditionally spontaneous? And so what I would say is, well, if both of them are positive, you can't tell whether it's going to be spontaneous or not. We said earlier that if delta H is negative and delta S is positive, it is definitely spontaneous at all temperatures. If the reverse is true, if delta H is positive and delta S is negative, it is never spontaneous at any temperature. But if they're both positive or if they're both negative, it depends on the temperature. Okay, and in this case they're both positive, so it does depend on the temperature. So this one is conditionally spontaneous. Okay, so then the question, or the last question we have to answer, says, if the reaction is conditionally spontaneous, determine under what conditions it would be spontaneous. So all that means is at what temperature or temperature threshold would it go from being spontaneous to non-spontaneous, or vice versa. Okay, and here's how we figure that out. If we want to know the threshold between spontaneous and non-spontaneous, that all depends on delta G. So delta G, and I've gotten a bit sloppy up above, so let me rewrite this. So delta G equals delta H minus temperature times delta S. and we want delta G to be negative in order for it to be spontaneous, positive for it to be non-spontaneous. Therefore, what would the threshold be between spontaneous and non-spontaneous? Okay, it would be 0, right? That's the threshold between positive and negative. It's 0. So what we're going to do is we're just going to set delta G equal to 0 and solve for temperature. Okay, so if we want delta G to be 0, so 0 equals, in this case our delta H was 850.5 kilojoules, and then we're going to say minus T, because we don't know that's what we're trying to solve for. So minus T times delta S, which was 0.038 kilojoules per Kelvin. And then this time I am going to ask you to go ahead and get out a calculator. It could just be on your phone or whatever, and see if you can solve for temperature. Keep in mind that that answer is going to be in kelvins. Okay, so there you see the math there, solving for T. Hopefully you got, that's what you got, 22,381 kelvins. I guess you could convert it to degrees Celsius, but you know, subtracting 273, you still got over 22,000 degrees. So it's extremely hot. So this just means that this reaction only is only spontaneous at extremely high temperatures. Well, actually, let me back up for a second. What we really found was not the temperature at which it is spontaneous, but we technically just found like the threshold between spontaneous and non-spontaneous. So how do we, what's really the best way to say this? Because technically at that temperature, 22,381 kelvins, delta G would be 0, right? Like that's by definition how we solve the problem. We set delta G equal to 0, which is neither spontaneous or non-spontaneous. It's like the threshold. It's the top of the hill. Spontaneous being on one side, non-spontaneous being on the other. So what this really means is if delta H and delta S are positive, when you get your answer in a problem like this, what you're solving for is the minimum temperature. So really, a better way of saying this is the temperature for this to be spontaneous would have to be greater than 22,381 kelvins. And hopefully that makes sense because, well, for a couple of reasons, but the biggest is that it's an endothermic reaction. So if it's a reaction that absorbs heat, it should hopefully make sense that it would be more spontaneous at a higher temperature. So there you go. It would be spontaneous only at or above 22, or I should say only above 22,381 kelvins. All right, so that pretty much takes care of our discussion of entropy, free energy, delta G calculations. What we're going to do next, or the next part of your assignment for that would be due next Wednesday, is actually going to be a preview of our next set of notes, our next discussion that I'll post next Thursday. And that preview is going to happen by way of this ck12.org website. Essentially, if you haven't used it before, it's basically like an online textbook. And since you don't have a textbook, I thought I would go this route. They have some pretty good materials. So basically, just think of it as, all right, you did the calculations, you did the ed puzzle, you reviewed what you'd already learned. So then now let's take a look at something new, and it's like you're opening a textbook and previewing the next lesson. So let me just kind of show you what this is going to look like a little bit. It just basically, again, it's like an online textbook. I will put links on Classroom. You should see them already. To the two sections I want you to read. One of them is on reaction rate. The other one is on collision theory. But basically, it's just like reading a textbook. You can take notes if you want to, but again, I'm going to give you my formal notes over reaction rate next time. And then, there's a little video. This guy does a great job. He's not in all the videos, but they have very good videos explaining in this case, rate of reaction. And then when you get to the bottom, they'll ask you a couple of review questions. You don't have to answer those in a formal way. It just kind of gets you thinking. And then you'll do this little practice. And it's not going to be for a grade, but I do encourage you to try those practice problems. I may put them into the Ed puzzle that I present next time as we go over this material. Um, and I'll probably start applying like an accuracy grade, or at least part of your grade for the Ed puzzle will be for accuracy, just to kind of encourage you to take those as seriously as possible. But the online book assignments, the two sections that I'm going to assign you, are when you do the practice at the end of those, that's just going to be for your benefit. Okay, so, and again, this will all be posted on Classrooms. You don't have to worry about writing this down right now, but it's just going to be sections 18.1 and 18.2 of a reaction rate and collision theory. So please don't hesitate to email me with any specific questions. And also, our first Google Hangouts Meet help session for you guys is going to be Monday morning at 11. Remember, that time changed from 3 p.m. to 11 a.m. And then we also have Wednesday afternoon at 3 p.m. So thanks a lot. You guys have a good weekend, and thanks for watching.